So the next part is about importing data into Blender. It's where you have existing files, for example HTF5, V2K, or maybe a tabular format like Excel or CSV, or one of the 3D formats that exist. You have data, you want to import it into Blender. And the first thing to think about is, what are your goals for the import? So once you have the data into Blender, what do you want to accomplish? And it could be as simple as taking the imported data as is, and maybe add some materials, some lights, and then do a render, or even making an animation out of that. Or are you more interested in analyzing the data? For example, looking at the meshes that you imported in detail, maybe doing a scientific visualization of the imported data. Or yet another option could be that you'd like to edit whatever data you imported, edit it within Blender, and then export it back to another file. And depending on what your goal is for the import, your workflow might need to be changed slightly. And the file formats that you use can also vary depending on what your goals are. So a second aspect to consider when importing data is, can you convert the data that you have into one of the available object types within Blender? And there's quite a few. Most of them are visible in this picture here. But most of the time, a polygonal mesh like this will do. However, not in all cases. For example, your data might consist only of 3D points. For example, if you have like a laser scan of some scene, and then you need to do some extra steps, as the 3D point coordinates only are not enough to do a render, as there's no geometry there. Another case that might need some work is when you have volumetric data. Although Blender has some support for volume rendering, for example this object over here, it is not as flexible as in most scientific visualization programs like ParaView. So depending on what data you have and what your goals are, you need to think about how to represent the data and how you need to do the conversion, if any. So a third question is, can Blender even import your files, and do you need to do some conversion first? Now luckily there's quite a few 3D formats supported by default, and maybe that's good enough. And some formats support extra options, for example storing per vertex colors or materials, but then you might need some additional feature that is not supported, for example storing a velocity vector per vertex in your data. And then you need to work around the limitation. And as we mentioned earlier, simply importing the data might not be enough. You might need to do some editing, for example simplifying geometry when it's too much, or combining different meshes into one. And then you have the option to either do that by hand or to script that in Python within Blender. And depending on your particular workflow, in your case, one or the other might be interesting. For example, if you need to do only one import of a file, then manually editing might be good enough. But if you have 1,000 files that you need to edit, then scripting becomes probably the only feasible option. So when it comes to importing into Blender, there's technically 3 options that you could use, but only 2 of them are practical. And the first one is to take advantage of the available formats that can be imported. And if your files are already in one of those formats, then it's of course simple. It's just a straight import using the file import menu. Or you might need to convert the data that you have into one of these formats and then do an import. The second option, if using the existing importers isn't good enough, is to write a small Python script that does the import for you. And this could be an option, for example, if you have data that you do not want to convert because it's maybe too large and you want to read from those files directly, or you want to do some processing during the import that you don't want to do by hand. So these are the 2 main options. And the third option, but technically feasible, would be to convert your data into the native .blend file format. Now this is not recommended. The .blend format is basically a memory dump. It's written in a pretty clever way to make sure that it works with every version of Blender. But writing that yourself or even using a library is just too much work in my estimation. By default, quite a good set of file formats is enabled for import. For example, GLTF, Stanford Poly, Wavefront OBJ. Those are well-known formats that are supported by a lot of programs for importing and exporting, and they support a decent set of features. And you can even enable additional ones within the Properties window under the Add-ons tab. Simply clicking the ones that you're interested in, and they will then show up within the import menu as well. And if the built-in add-ons are not enough, you can go online, find third-party add-ons, for example, the Blender GIS add-on, which is nice if you work with, say, OpenStreetMap data, and it allows you to directly load into geometry from OpenStreetMap into Blender. There's quite a few of these third-party add-ons that you can install without too much trouble. So here's an example of getting data from one program into Blender. And in this case, this is ParaView. You've got a 3D model loaded here. And this is actually a scan of a real statue. And when we look a little bit closer at the surface, we can see that the triangle size varies quite a bit. So we've got very large triangles, very small ones. And one thing you can do in ParaView is visualize the difference in triangle area. And I've got that prepared here. So if I enable that, you can now see that the triangle area is used to color each triangle. And this goes from the blue for the relatively small triangles to red for the relatively large ones. And most of this looks okay, but if we go to the backside, then over here there's a couple of triangles which are quite large. Now suppose that we wanted to export this model using this coloring into Blender. For that we can export it through the Save Data function in ParaView. And this gives us a number of file format options. But there's actually only 3 of these that are supported by Blender directly that it can read. And the first one is PLY, the second is STL, and the third one is wavefront object. Now wavefront is a text-based format, so it's quite large, especially for a file like this, so we'll not use that. STL does not support storing a color per vertex, so that doesn't work either, so that leaves us only with PLY. We'll overwrite the existing file that I did earlier. The exporter within ParaView has got quite a number of options. The most important ones in this case are to choose the binary type of PLY. It also has an ASCII format, which is a lot larger. And we need to enable the coloring in order to store these colors per vertex. So that was done in roughly a second. And now we can go into Blender, use the file import menu, pick PLY, pick the file that we just wrote and import it. Now this actually takes quite some time. And the reason for that is this is a large file. And most of the Blender import scripts are written in Python. Although there is some effort going on to turn them into C++ for speeding them up. But this is done. We can see we've got a new object, although it's not visible. But if we press home to zoom out, we can see that it's there. And apparently the scale of this model within this scene is not exactly what we expected. It's much larger. The other thing to note is that its orientation is different. And the reason for that is that in ParaView, the y-axis is up, while in Blender, the z-axis is up. So looking at the details of this mesh, it indeed has a vertex color layer called Col. And I prepared a material that can use these vertex colors. So if I choose that, and we visualize the colors again, you can see that this matches what we saw in ParaView. So in this way, with just a few simple steps, the data gets from ParaView into Blender, and you can work from here. And one thing that you could do, because this is Blender, is to go into edit mode on this mesh, which we haven't shown before. But this basically allows you to edit all the vertices and even the colors in this case, if you'd like to. Something that isn't possible within ParaView. So as mentioned earlier, the different file formats that are available for import differ in the features that they support, but also in how you work with them, what their strengths are and what their weaknesses are. So here's a table that tries to summarize that to some extent. So the first column is whether the file format is only in a binary form or also supports a text form. And this matters for the size of the file that you work with. The text form is usually a lot larger, but also how fast you can process this. Again, the text form is usually slower. There's a column for whether a file format can contain materials, whether it can contain multiple objects or say just one mesh, whether the file can store vertex colors, textures, and the final one is how difficult it is to write a certain file format. And writing here means implementing the writer yourself, so not using a library. For example, you have some simulation code and you want to output in one of these formats directly, then how much effort does it take to write it? Now overall, You can see there's quite a bit of variation, and some of this is subjective, of course. But I would say that GLTF, which is a very modern format, very flexible, is a good one if you have a more complex scene. For example, multiple objects, advanced materials, etc. It's a little bit harder to write due to the way that it's structured. It supports triangles only, so that can be a limitation. But overall, this is quite a nice format. And if you have only a single mesh, for example with vertex colors, then the PLY format is quite nice. It's a very simple header that you write and then just dump the raw data to disk. It also supports general polygons, so not just triangles, but also quads or any n-gon actually. And the other formats are not useless, of course, but they're slightly less easy to work with or larger on disk, etc. And then there's also some differences between the importers within Blender. So when you open an importer through the File Import menu for a specific format, each format will have a different set of options that you can use during the import. For example, you might want to scale the file during import. You might want to flip the axis to change the orientation, etc. And depending on the file format you've chosen, you can see that the options differ here. So this can influence your workflow a little bit because certain operations might be doable through the import options. In other cases, you might have to, for example, rotate the model after you've imported it manually. So it differs a little bit in how you work with the file format, what you can do with these options. And then depending on the file format, the size on the disk and the time it takes to import a model can vary quite a bit. So here's an example. It's a little test with the Suzanne model, the monkey head, converted into 1 million triangles, and then exported to the different file formats, and then re-importing them back into Blender. As you can see, the file size already differs quite a bit. So the smallest one is GLTF in the binary form. It takes around a second to import, while the slowest one is FBX, which is twice as large on disk, and it takes more than 6 times as much time to import. If you have only one file that you need to import, this doesn't really matter, of course. But if you want to import thousands of files, for example, for an animation, then these kinds of differences can add up, both in disk space that is used as well as in time the total import takes. So that was quite a lot of information on the different file formats that are available within Blender for importing, and details on the formats themselves. And hopefully this will give you enough information to make a choice between these formats, to do some experiments to see what works best in your case. Now, as we mentioned all the way in the beginning, there's a second way to get data into Blender, and that is to use the Python scripting API. We won't go into Python scripting within this basics course. We have a module on Python scripting within our advanced course later in this year. So if you're interested in this topic, then we suggest that you follow the advanced course. But briefly, one of the nice things of Python scripting for importing is that you can do more within such a script than just read in the data and turn it into, say, a mesh. You can do all kinds of processing on the data, combining meshes, for example, or setting materials, and doing stuff that you otherwise need to do by hand within the script. The available importers within Blender are written in Python as well. They're distributed with Blender, so you can use them to learn from the code in there or to base your import script on the code. One of the downsides, of course, that you need to learn how to program in Python, and this might not be the biggest challenge. Usually the Blender Python API is the real tricky part there. It's a bit difficult to understand how it works, but once you've learned it, then it becomes easier. Of course, writing a Python script is harder than just doing the import using the file import menu. And in general, if you have really large files that you need to process in pure Python, that will be slow, although there's some ways to speed that up. So here's an example from one of our own projects where we had a very large simulation of red blood cells. Each cell is a small piece of geometry, and together these cells form a very large system. There were many time steps, and each time step was saved to multiple files because this was computed in parallel over multiple compute nodes. So each file would contain a part of the simulation for a single time step. Now this was saved all in HDF5 format by the simulation, and HDF5 is used quite a lot in a scientific context, but Blender obviously cannot read those files directly. Luckily, there's an H5Py module for Python that can read HDF5, and we could write a small import script, blender import.py, that used this module to read the data directly from those files, combine them into a single mesh within Blender. And the script could do a few other things, for example, set the material automatically, in some cases set a few lights, so it prepared the scene for rendering all from the import script. Another option that it could do was take the cells at the positions that they were in the simulation, but instead put them side by side. So this was one way of visualizing all the cells within the simulation. And as you can see, this is a pretty powerful approach because you can script basically anything within the Python script, but it does add a bit of complexity in having to create it and having to debug it, etc. So one thing that we mentioned earlier is that it can be a bit of a challenge to match whatever data you have with what is available within Blender in terms of scene object types. Things that are easy is when you have 2D or 3D geometry, polygons basically. Those you can import without too much trouble, usually using the right format and the right options. One exception to such services is finite element style meshes, for example a tetrahedral mesh. Blender cannot represent such a mesh, it simply does not have the data structure for that. So you need to figure out how to deal with that. And one way could be to extract the surface of the mesh and then import that within Blender. Slightly more work, but still doable, is when you only have point coordinates, for example a laser scan, and even point coordinates that have associated values like a per vertex color. Those can be imported and represented without too much trouble. When it comes to volumetric data, and we'll look at that in a moment, usually the options within Blender are limited. For example, there's no adaptive mesh refinement type, or things like cylindrical coordinates. You simply cannot represent the data. So again, you need to figure out how to work around that issue. And finally, if you have arbitrary values on the vertices, for example, a velocity vector, again, there's no way to represent such a value within Blender. It basically only knows about vertex colors. So you might need to strip away those velocity vectors. You might need to convert them yourself into colors first before importing, etc. So another challenge has to do with very large data sizes. Can Blender handle those? Can your system handle those? For example, if you have very large meshes, let's say tens of millions of polygons, will that work? Or when you have smaller meshes, but you have thousands of them in a scene, can you still interactively view such a scene? Can you still edit such a scene? Well, the answer here is it really depends on what system do you have, what GPU do you have, how much memory do you have. In general, you can say that a few million polygons within a single 3D mesh should work on a modern system with a good GPU. When you start to use something like 50 to 100 million polygons, that's already stretching it a bit, especially if you want to interactively edit such a mesh. Having thousands of objects within a scene is also usually a bit tricky. Hundreds should be no problem, but thousands, especially if they're more complex, then that becomes already a problem for just viewing the scene interactively. So here you might have to adjust what you're doing already in order to even work on the scene. So one way to handle these large datasets is to simplify it before import, reduce the number of polygons or reduce the number of objects as a way to simplify the scene. Another is to have a better GPU in your system, if that's even possible. Use a system with more RAM, or if you can set up the scene using a stand-in object like a proxy that is a low resolution or just a subset of all the objects, then you can set up the scene like that and then during rendering use the actual objects in full resolution and all of them. Usually that takes a bit of Python scripting, although you could do it by hand, but it's one way to handle these complex scenes. And usually there's a third set of challenges that you run into. For example, the model scale that you have might be completely different than what Blender is used to. Let's say your data is stored in unit meters, but your coordinates only start at, say, around a million to 2 million, for example. If you import that in Blender, then you will probably not see the mesh, or it might only show part of it. And one of the reasons for that is that Blender more or less assumes that you model things around the origin, so around 0, 0, 0, and don't have coordinates that are too large. Another issue could be that the data that you have is represented in double precision floating point, because that's what your simulation or your data needs, while Blender internally only works with a single precision float. So you would need to scale and convert the data first into single precision floats that still make sense, and then import them. Usually there's also a mismatch in coordinate system. For example, the up axis is different, where it's Z in Blender, it could be Y in your own software. Or your model is mirrored along one of the axes because the data that you used a left-handed coordinate system versus right-handed coordinate system, etc. And there's all kinds of other problems that you could run into. Unfortunately, most of this is just experiencing it and trying out if the data imports correctly, and then see if any of these issues occur and how you can handle those. So let's look into detail into a few of the different data types that you might want to import. So we'll start with point data. Usually get this type of data within Blender isn't an issue. You can use one of the available file formats for 3D meshes and only store vertices, for example XYZ values, in a PLY file, and then import that. And that will give you the vertices within Blender in a mesh. But vertices alone is a geometry, there's no polygons there, so it won't render anything. One way to handle that is using so-called instancing. That's where you have your point cloud, and you take a very simple object, usually a sphere or a box or something like that, and then place such an object on each position of a vertex. And that gives you geometry that represents your point cloud. And then you can process this in any way that you like by assigning materials or scaling these spheres or shapes in any way, etc. This is actually quite easy to do. Here's the recipe. It's just 5 steps, and then that gives you this result. And the nice thing of that is if you do this type of instancing, you can still edit the shape that you place or even the point cloud itself and see what the results are. So we'll just have this recipe here as a reference in the slides. We won't go into that in detail. Usually when you have point cloud, there's some values that you associate with each vertex. For example, a density value, a velocity vector, or maybe there's a color already. There's no support within Blender for handling arbitrary values. It simply cannot represent them. There's basically only a per vertex color. So you need to think about how to handle that. So we can hack those values within the scene, for example, by misusing vertex colors to store whatever value you have. So you could convert your velocity vector into 0 to 1 for each of the 3 coordinates, and then color your mesh based on that. Or you could use texture coordinates, so-called UV coordinates, for 2 floats. You could even store some data in a custom property in Python. But you need to do this mapping from the values that you have into colors somewhere, and then use the colors that you compute in the rendering setup. There's a better solution, and that's to do the color mapping in an import script. So you can map whatever value you have into a vertex color, store that in the imported data, and then go from there in the normal rendering workflow. And we have an example of how to do that in one of the assignments. Another type of data that is used frequently within a scientific context is volumetric data, for example for a fluid simulation or for a medical image. The current support in Blender for volumetric data is fairly limited compared to the average scientific visualization package like ParaView. In Blender, volumetric rendering is mostly aimed at visual effects, for example cloud or smoke, but the available infrastructure can be used for other types of data and use cases. There's a dedicated volume object that you can add to the scene. You need to load the data from an open VDB file and then render, and there's a limited control over how you make the data look within the scene. So here's an example where we took an existing data set, a CT scan of a mummy's head. We converted the data from a native format that it was into a VDB file using Python, imported that within Blender, and then set up a shader over here to make it look the way it does over here. And this shader basically uses 2 components. One is to determine the color of the volume based on the value within a particular position within the volume. This is this shading node over here. And the other is to change the opacity of a point within the volume, again based on the same value. And by combining these 2, we can render an image like this. So the OpenVDB file format, that is the basis of volume rendering within the current version of Blender, is a so-called sparse voxel tree representation. So you can have a regular grid of voxels where parts of the data are basically 0. Those then get stored very efficiently, so you get a small file for a sparse volume. Now VDB originates from motion picture rendering, again things like clouds. So there's a couple of limitations. One is that it's only suitable for rectangular grids, so there's no adaptive mesh refinement. You cannot do cylindrical coordinates and stuff like that. You can have different scaling in X, Y, Z, but you can't have non-uniform scaling along one axis. So for certain simulation types or data types, that might be a limitation that you need to overcome. So you might need to convert your data first or resample it to a regular grid. One challenge here is how do you write these VDB files? The options there are a bit limited. One is to use the Python bindings that are available, called PyOpenVDB. They support efficient conversion from NumPy arrays into a VDB file. Software like ParaView is slowly adopting a VDB writer, although that's not available yet, but it will come at some point. Then the rendering of volume data within Blender is based on shading on a 0 to 1 range. So if the values that you have within your volume do not match the 0 to 1 range, you will need to map the data in some way, either during the import or in the shader. You can edit the way the volume is rendered using these color ramp nodes that I just showed for the color and the opacity. It's a bit different from having a transfer function editor, for example, in ParaView. The results might not be as good as you get it in ParaView, but it's still something. And also the volume rendering within Blender doesn't appear to be very fast compared to something like ParaView. Now one option, if you want to avoid all of these issues, is to take your volumetric data and then extract non-volumetric data, for example an ISO service like this, and then import it as a regular polygonal mesh and go from there. Of course, that might not be something that you want to do, but it's always an option. So finally, we've shown a lot how to import data into Blender. As we said in the beginning, the first thing to think about, what is the goal for your import? What do you want to accomplish? And then what object types do you need? How are you going to approach getting the data into Blender, etc. So the exercises within this module are basically about that. If you have own data that you want to use, try to think about these things. And then maybe even try to import the data by making a conversion or doing a small test file. And if you do not have your own data, you can do the importing data exercise, which provides a file containing geometry with vertex colors and in a different format, and then see how you can import that into Blender. So for reference, we provide within these slides some notes on ParaView and Visit, how to get data from those two packages into Blender. So there's notes here on what options you need to use within ParaView, for example. The other is for VTK. Again, a set of reference slides for the different VTK filters that are available and how they write the data as output and how you can use that within Blender. So please check these slides for these references.